we want to get to the mathematical details of the work done by the spring. And the first thing that we have to do here is that we have to deal with something called Hooke's law. And then once we deal with Hooke's law, you're going to find here that this is a variable force. So this is a big deal. This is the first variable force that we've encountered in Physics 11. And it turns out that because it's a variable force, we do not have the ability to deal with this mathematically. The only way we can solve spring problems, if we tried to use Newton's second law to calculate acceleration, it would require differential equations. And this is Math 7, which is well beyond the scope of this course. So you cannot use Newton's laws to actually solve this, not even in 4A. But what you're going to find here is that when we go to look at the work of the spring, what we'll do here is that we will deal with this mathematically by calculating areas. That's how we can deal with the spring. Otherwise, it's mandatory that we deal with the mathematics of it. So let's deal with Hooke's law first. So the first thing that we want to do is we want to deal with Hooke's law. Hooke's law, it describes how a spring force comes about. And what it says here is that the force of a spring is equal, which we call Fs, is equal, and this is an important thing, there's a minus sign right there, and it has two terms. It has a term called K, which is called the spring constant, and the change in displacement. So this right here is Hooke's law. Now, once again, this force is not constant. So we have to deal with these two terms. So the two terms of the force then go like this. So the first one that we need to deal with is we need to deal with what is called the spring constant. And it turns out that experimentally, there's a difference between a physics spring and an ideal spring, a textbook spring. In a classroom, lecture room, we deal with a textbook spring, but they don't exist in real life. Physics springs, real springs, they only go one direction, which is a little bit tricky to think about that. So what is a spring constant? It tells us about the strength of a stretching a spring or changing its distance here. So picture-wise, what we could imagine here is that if I have a strong spring, now what would be a strong spring? What about a car spring? Like a car shock system. So a car spring, those guys are very strong springs. And so what you're going to find here is that if you have a strong spring, that means it's hard to compress or stretch. Now remember, this is
I have a question.
This is a physics spring. A real spring. Yes, go ahead.
So when we're talking about springs, right? I don't know if this is beyond the scope of the course, but how do you look at certain liquids when they compress and decompress as springs?
Liquids are easy in that sense because liquids you can't compress. Like you can take water and you can try to compress it, and it's only a tiny fraction of a percent that it even compresses. Whereas a spring
because I know
will literally compress.
because I know with some suspension systems they use hydraulic oil.
But by the way, that's not a compression.
Okay.
Okay. So it's hard to compress, and therefore, because of this, they have a large spring K value. On the other hand, if we have a weak spring, and the weak springs are the ones that these are the so-called lab springs, the ones that we've used multiple times. These guys are easy to compress. And because they're easy to compress, they have a small K value. Now, the other thing here that we should look at here is that the compression stretching distance is what we call delta K. Now, remember, the spring force is a variable force. Okay, it's a variable force. So let's think about this picture-wise. So I'm going to hang a spring, and I'm going to put it into an equilibrium state. So as an example, I'm going to hang a mass from a spring. So I imagine that I have this. Let's say that this is a ceiling or some type of clamp system. And then right here, I'm going to put my block here. Here's my mass right here. And what I'm going to do here is that if I just let this hang, what you're going to find here is that if I focus on the center of mass, this point right here, we call the equilibrium. And why is it an equilibrium? Because here we have a balance of forces. So in this case, we're going to have a spring force that pulls up, and I'm going to say that this guy is going to be the force of gravity. So in this case here, we know that the net force here is equal to 0. At this point, this is what we call x equal to 0. So now we're going to do this here. So now I'm going to take this spring and I'm going to pull it down from the equilibrium point. So if I do that, let's say that I only pull it this far down, right here. And so when we measure the distance of how much this spring has been, stretched in this case, then we say that this distance from here to here is our distance delta x. So that means our spring force, in this case, is now going to be larger than at the equilibrium point. So now I'm going to see that I'm going to have a spring force that's going to point in that direction like that. And by the way, I did not say this, but I'm going to say here that the displacement is going down. Now what I'm going to do is that I'm going to stretch the spring even more so. So in this situation, I'm going to take this block and I'm going to stretch it all the way down to here. So conceptually, you have to agree that if I take an object like this and I pull it down more, that this guy pulling it down more from the equilibrium point has to be a bigger force. Your experience is that this force here is going to be larger than before. So when I go and I compare this, and we ask the question, why is this larger? And the reason why is because our displacement is larger. And what you're catching here is that you can see that from here to here, that there's a difference in forces. And that implies it's a variable force. I have to pull harder on the bigger distance here. So when I go look at the magnitude of the spring force, we could see that in each case, even though they're the same springs, the fact that I pull this guy down only a little bit and this guy even more so, that tells you that this is a smaller force and this guy is a larger force. And therefore, that's what we mean by a variable force. There's a change in force and its relative distance. So as I stretch this thing, if I call this, state number 1, and I call this number 2, the amount of work to stretch 2 has to be greater than the amount of work done to stretch 1. So here we go. So by definition, here's what we know. So the work done by an external force is the area under a force versus displacement curve. So in other words, the work has to be the area very similar to, I'm going to take that off, very similar to what we saw with the impulse. Impulse and work are very, very closely connected. So this is the area of F versus X curve. And what we find here is that if you've had a little bit of calculus, you would find that what we're really seeing here is that we're seeing a curve. And as I look at this curve, if I have any shape of a curve like this, and if I calculate what this area is, if I could parameterize this curve, then this area right here is what we would call the work. So we can do the same thing with the spring force. So to calculate the work of the spring, we plot F of spring versus X. And here's what we see here. So when I plot this guy, I'm going to have a curve here. And the spring force is equal to minus kx when this is x. So as a consequence, I could now, you could see that this is a negatively sloped line. So if I was to draw a curve here, then it's going to look something like this. It's going to be a linear line like that. And so picture-wise, let's see if we can understand what this area actually means here. So what I'm going to do here is that I'm going to try to set up a picture. So now imagine this is the picture here. So so this is a physics spring. This is not a real spring. This is a theoretical spring. So here's what I'm going to show you here. So this, I have a spring that's attached to a block. And what you're going to find here is that if I look at the center of mass right here, this is the location that we call x equal to 0. So this point right here tells us that this is x equal to 0, and this is the equilibrium. In other words, this is an unstretched spring. Now what I'm going to do is that I'm going to now expand this thing. So as I expand this guy and I move it away to this location, what you're seeing here is that, you know what, I'm going to call this point right here x1, just for the sake of argument, because it's going to be easier mathematically to deal with this. So now, here's what I'm going to do. Then this guy, I'm going to move to x2. So as I move this guy in there, what we see here is that there is a spring force that moves in this direction as my displacement goes in that direction. So what you're seeing here is that the distance from here to here is then going to create a difference in this displacement. So if I go to this point here, let's say that this point, I'm going to call this point right here x2. This point is going to be x1. Then you can see here that the area of this curve is half of a rectangle. So we could see here is that this area is half a rectangle. So I can calculate that. So according to this thing here, what does it say? I have that rectangle and it looks something like this here. So now, calculating the area implies that when I look at my line, I have a triangle. And what I'm seeing here is that I have moved this thing a distance x from there to there. And then this height change is negative because this is the spring force, which is minus kx. So if I look at the area of this guy, the area of a rectangle should be the height, right? So now if I look at the area, it should be 1/2 the height times the base. And so when I add this all up here, you're going to see that this will then be 1/2 times minus kx times x, which then gives you minus 1/2 kx squared. So that is going to be my area. But let's be careful here, because I have to adjust x right here. Okay, we have to adjust, because what we call this here is we call this point x1, and we call that point x2. So it's really, so if I make an adjustment, what this really says is that it's going to be minus 1/2 kx2 squared minus 1/2 kx1 squared. So now if I put this all together, because this expression comes up so often when dealing with springs, we write a shortcut in notation. So then we say this, that by definition, the negative work of the spring we said was equal to the change in potential energy of this spring. But we just calculated the work here. So if we calculated the work, then coming right from here, we could see that I'm going to get a minus here. I have a minus already, but then the work of the spring also carries a minus sign, which then tells us it's 1/2 k x2 squared minus 1/2 k x1 squared. And you can see here is that this guy and that guy cancel out. So therefore, we could then write that 1/2 kx squared minus 1/2 kx squared is equal to the change in the spring potential energy, which is also equal to the negative of the spring work. This is what our potential energy is right here. So remember, this guy is exactly the same as work. So when I look at this thing, is that we redefine the work term. And we then say that this negative work of the spring, which is equal to 1/2 kx2 squared minus 1/2 kx1 squared, we define this as u2 minus u1, which is then the change in the spring potential energy. So what does this mean? Well, this by itself is meaningless. That by itself is meaningless. Only this guy is meaningful, which is pretty tricky because there's this minus sign that is floating around. But that's what we mean by the work energy theorem becoming a different type of energy.